Many properties of solutions depend on what the solute is and what the solvent is. However, there are four properties that are independent of what the solute is. It just depends on how much solute you put in, and those are vapor pressure, boiling point, freezing point, and osmotic pressure. When one makes a solution by dissolving a solute in a pure solvent, you would expect the properties of that solution to be different than that of the pure solvent, and most of the time they are. There are some properties, however, that are independent of what type of solute you add and only dependent on how much you add. We call those properties colligative properties, and the definition would be properties that depend only on the amount of dissolved solute and not on the solute's chemical identity. So if by adding a solute to a solvent, there are four different colligative properties that we talk about in this section of Chapter 11. That's vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. When we think of vapor pressure lowering and boiling point elevation, we can actually experience that in our kitchens, where we literally add salt to water to raise the boiling point or lower the vapor pressure. Or if you're an ice cream enthusiast and you make your own ice cream, we add salt to the water around the container to lower the freezing point so that we get colder ice cream. And finally, osmotic pressure. That's how we carry liquids and oxygen around in our bodies through the red blood cells, where we generate a pressure, so we have blood pressure. Let's start off our discussion on colligative properties by discussing vapor pressure lowering. So what is vapor pressure? If we place the liquid in a closed container, we will be vaporizing some of that liquid into the gas phase, and we will be condensing some of the gas down into the liquid phase. When we reach an equilibrium, we have an equal amount of liquid turning into gas and an equal amount of gas going back into the liquid. So if I look at this graphic down here, I have liquid molecules there being vaporized into the gas phase, and I have vapor molecules, gas, being condensed back onto the liquid phase. These molecules that are in the gas phase, they actually bump into the walls of the container, and we know that that exerts a pressure on that container, and we could hook up a manometer and actually measure that pressure. So the vapor pressure of a liquid is the pressure exerted by the gas molecules when the liquid and the gas are in equilibrium. Another way to look at that is down in this graphic here, where I have pure solvent down here. I have a sealed container. I have some gas molecules that have been vaporized. They bump into the container again and exert a pressure. Let's now add some solute to my liquid. So my solute molecules actually reduce the surface area at the top of the liquid here. So I have fewer molecules that can be actually vaporized. That however, has to assume that my solute is not going to be volatilized, so it's a solid and dissolved in solution. So what that has is an effect on the vaporization rate. The rate of vaporization decreases. The rate of solvent condensation remains the same. So if I look at this graphic over here, I have fewer molecules going into the vapor phase, but I have the same amount still going down, condensing back into the solute, because only the volatile solvent molecules can be vaporized. So the presence of non-volatile solutes, like these green spheres right here, or these blue ones in this picture over here, it lowers the vapor pressure by impeding the evaporation rate of the solvent molecules. That's how we can actually sort of describe vapor pressure lowering, by adding a non-volatile solute to a solvent. Raoult actually came up with a relationship between the partial pressure of a gas and how much solute is actually added. So what his relation is that the partial pressure of the solution is equal to the initial partial pressure of the pure solvent, that's what this little superscript 0 means, pure, times the mole fraction of the solvent. So what is the mole fraction? We've talked about molarity. That's just the moles of solute divided by the liters of solution. The mole fraction of a solvent is actually equal to the moles of the solvent divided by the moles of the solvent plus the moles of the solute. So that's how we're defining that. And we're going to use this mole fraction when calculating the partial pressures of a solution using mole fraction here. Let's now look at Raoult's law in graphical form. Here's his law again. The partial pressure of the solution is equal to the partial pressure of the pure solvent times the mole fraction of the solvent. In this diagram here on the left, I have a sealed container with a liquid in it. I wait until I actually reached an equilibrium of evaporation and condensation, and then I measure the pressure using a manometer. And this graphic just shows sort of a relative pressure here on this red line here. If I add some solute to my liquid, as shown here by these red spheres right here, these are non-volatile solute molecules or atoms. If I then wait and I measure the pressure again, I see that my vapor pressure is lower. So in other words, the pressure of my solvent is greater than the pressure of my solution. And that's Raoult's law, and it's related to the mole fraction of the solvent. We have seen that the partial pressure, based on Raoult's law, is a colligative property that is directly proportional to the concentration of the solute particles. It doesn't matter what those particles are. For example, by dissolving 1 mole of glucose, C6H12O6, which is a non-electrolyte, that results in 1 mole of solute particles in my solution. However, if I dissolve an electrolyte like sodium chloride, for example, I take 1 mole of sodium chloride in and dissolve it in water, I actually get 2 moles of solute particles because I get sodium cations and chlorine anions. I get 2 particles in my solution now, and we need to correct for that. The Van Hoff factor, which we're going to call this little small italics I here, is the ratio of solute particles in solution to the number of formula units in solution. So for example, For sodium chloride, that I is going to be 2. So I take sodium chloride, I dissolve it in water, I get 2 moles of my ions or particles in water. If I take my glucose, dissolve it in water, I get 1 mole. If I take calcium chloride, I take 1 mole of calcium chloride, dissolve it in water, I get 1 mole of calcium and 2 moles of chlorine for 3 particles or 3 moles of particles in my water. And as another example, sodium phosphate, if I dissolve that in water, I get 3 moles of sodium and 1 mole of phosphate for a total of 2 moles of particles in my water. So you can see we need to correct Raoult's law depending on which type of solute we use, whether it is an electrolyte or a non-electrolyte, but we're still thinking only these colligative properties depend on the number of particles in solution, not what they are. So let's look at that Van't Hoff factor, this italics I. That's the moles of particles in solution divided by the moles of solute in solution. For example, if I put a mole of sodium chloride, I'd have 2 moles of particles in solution. If I took 1 mole of glucose, I'd have 1 mole of particles in solution. So we need to include this correction factor in all colligative properties and equations, even beyond our partial pressures. So here's Raoult's law again. We're now going to correct my mole fraction using the Van't Hoff factor. So my mole fraction in this case is still my moles of solvent, divided by my moles of solvent plus my moles of solute, how much particles I've added, times that Van't Hoff factor, which is going to be like a 1 or a 2 or a 3 or a 4. If I go into the laboratory and I actually measure the Van't Hoff factor for strong electrolytes, it turns out that my experimentally measured values are slightly lower than predicted. For example, for sodium chloride, we would predict a Van't Hoff factor of 2. That's because 1 mole of sodium chloride gives me a mole of sodium and a mole of chlorine for 2 moles of particles in solution. However, if I do the experiments, my experimental value for the Van't Hoff factor is actually 1.9. Okay? And what that implies is that there is some incomplete dissociation. Not all of my sodium chloride actually dissociates into 2 particles. Let's look at some other Van't Hoff factors, what we predict and what we actually measure. So if I take glucose, I would predict a Van't Hoff factor of 1, and I go into the laboratory and I measure it at 1. Sodium chloride, I predict 2, and I measure 1.9. HCl, I would also predict 2 because it's a strong electrolyte, and I measure 1.9. If I look at the strong electrolyte magnesium sulfate, I would predict 2, but I actually measure 1.3. Magnesium chloride, predict 3, get 2.7. Ferric chloride, predict 4, I actually measure 3.4. So the Van't Hoff factor is not perfect. However, we can actually rationalize that again by incomplete dissociation. And let's look at that. So what does that mean? The explanation for incomplete dissociation comes from the formation of cation-anion pairs. For example, if I put potassium chloride in water, potassium chloride is a strong electrolyte. It should dissociate into potassium and chloride. But because the potassium has a positive charge and the chlorine has a negative charge, they can actually pair up. Most of them are actually just separate ions in solution, like this chlorine, potassium, potassium, chlorine. There are a few that pair up. These act as one particle, so they've paired up. So the effective concentration of my particles, known as activity, is less than the predicted concentration of the ions in solution. Dissociation of ionic compounds is always not complete just due to this formation of these ion pairs, which accounts for my slightly lower Van't Hoff factor than predicted. If I were to take a solution and add a solute to it and then measure the boiling point or the freezing point, those are also affected by the solute concentration. In this case, a solution boils at a higher temperature than that of the pure solvent. So if I add a solute to a liquid and I measure the boiling point, it boils at a high temperature. The difference in boiling point of the solution versus that pure solvent is called the boiling point elevation temperature, or delta T sub B. A solution actually freezes at a lower temperature than that of the pure solvent. So the difference in freezing point between a solution, in which I've added a solute, and the pure solvent is called the freezing point depression, or delta T sub F. For non-electrolytes, those that do not dissociate, there is a relationship. Though that amount of temperature increase is equal to a constant, which is based on the solvent, times the molality of the solution. If I look at solutions made with electrolytes, I need to include the Van't Hoff factor because I know that they dissociate into more ions than moles of material. In that case, my difference in boiling point temperature is again going to be equal to some constant based on the solution times the molality times the Van't Hoff factor. The freezing point depression, that change in temperature, is going to be equal to minus a constant based on the solvent times the molality. And for electrolytic solutes, those are going to be equal to minus another constant times the molality times the Van't Hoff factor. Let's look at a table which actually gives us the boiling point constant and the freezing point constant for a variety of common solvents. For example, if I look on this table, benzene has a boiling point constant of 2.6 and a freezing point constant of 5.07. For all of these happen to be organic solvents. A lot of the chemistry that we do is actually based on water. So the boiling point constant for water is 0.51 and the freezing point constant is 1.86. Let's work out another sample problem. In this example, what is the freezing point in degrees C of a solution prepared by dissolving 7.0 grams of magnesium chloride in 110 grams of water? There's a few things I need to know. I need to know the freezing point constant of water, and I went and just looked that up in a table. I need to know the Van't Hoff factor. I could estimate it to be 3. But I'm also going to go look that up in the table to be more accurate. It turns out in this case, the Van't Hoff factor is 2.7. So the first thing I need to do is get all my units into moles here. So I'm going to take my 7 grams of magnesium chloride, convert that to moles by using the molecular weight of magnesium chloride. I have 0.077 moles. I then need to calculate the molality, my small m. Okay, so that's going to be the moles of my solute in kilograms per kilogram. So I just take that, I have 0.0076 moles. I'm going to put that in 110 grams of water. I'm going to convert that to kilograms of water. So in this case, my molality is 0.71 moles per kilogram. And then I can put it into my freezing point depression equation. So delta T, the change in temperature, is going to be equal to my constant minus 1.86 times my molality times my Van't Hoff factor. I do the arithmetic. That's equal to minus 3.6 degrees. Remember that that's just the change in temperature. I still need to actually go back and figure out what the temperature now is for water. My freezing point for water is 0 degrees. And once I've added my solute, it's going to be 3.6 degrees less. So I got to do a little arithmetic. My temperature for freezing now is going to be minus 3.6 degrees C. Let's do another example. What is the freezing point in degrees C of a solution prepared by dissolving 17.1 grams of sucrose in 200 grams of water? What's the freezing point of pure water again? That would be 0 degrees. So we're going to calculate the change in temperature. If I look at the Van't Hoff factor for sucrose, it is equal to 1. And again, my freezing point constant is minus 1.86 degrees C kilograms per mole. I'm going to calculate how many moles of sucrose I have. So I take my grams of sucrose divided by my molecular weight of sucrose. I get 0.0500 moles of sucrose. I now need to calculate the molality of my solution. That's my moles of solute divided by my grams of water. I'm going to convert that into kilograms because the definition of molality is moles per kilogram. I end up with 0.250 moles per kilogram of solute. Put that back into my freezing point depression equation. Minus 1.86 times 0.25 times my Van't Hoff factor. I get minus 0.465 degrees C. I need to subtract that from my original freezing point of water, so it's 0 minus 0.465. My freezing point of water now is minus 0.465 degrees Celsius. Let's look at an example where we actually calculate the boiling point elevation. So what is the boiling point, again in degrees Celsius, of a solution prepared by dissolving 20.1 grams of a non-electrolyte? That tells me something. If I have a non-electrolyte, I can actually assume my Van't Hoff factor is actually 1. We're going to dissolve that non-electrolyte in 400 grams of water. This material has a boiling point constant of 0.51 kilograms per mole and a molar mass of 62.0 grams per mole. So I need to know the information so I can calculate the molality. So I take my 20.1 grams, I know my molecular mass, I calculate the number of moles of solute, I then calculate the molality of my solution, taking my moles of solute divided by my water, multiplying times 1,000 grams per kilogram to get in the right units for molality. I have 0.810 moles per kilogram of solvent. I then put that into my boiling point elevation equation. And in this case, I got 0.51 times 0.810 times my Van't Hoff factor of 1. I get 0.41 degrees. What's the normal boiling point of water? That's 100 degrees, so I need to add my difference onto that. That means I'm going to have now my water is going to boil at 100.41 degrees. How does one explain the fact that adding a solute to a solvent elevates the boiling point and lowers the freezing point? It turns out that boiling point, delta T sub B, and freezing point, delta T sub F, are both directly the result of vapor pressure lowering. For example, if we look at boiling points here, boiling occurs when the vapor pressure equals the atmospheric pressure. And we know that vapor pressure is directly proportional to temperature. We can look at that down here on this graphic down here. If I have a pure solvent, I actually have a partial pressure of my solvent. When I start heating that solvent up, at some point my partial pressure of my solvent is going to equal the atmospheric pressure, and that's when boiling occurs. If I actually add some solute to my solvent, I know that the vapor pressure of that solution now is actually lower, so I've lowered the vapor pressure. I need a higher temperature now to actually equal the vapor, have the vapor pressure of my solution equal the atmospheric pressure. Therefore, my boiling point has increased. We can also explain freezing point depression and boiling point elevation using a phase diagram. So below here is a phase diagram where I've plotted pressure on the y-axis and I've plotted temperature on the x-axis. This red line here is actually the phase diagram for a pure solvent. So here's in this area here, I'm all solid. Here is the liquid phase, and here is the gas phase. If I were to add a solute to my liquid, I lower the vapor pressure, so I lower the pressure here. So this new green line here is actually the solution phase diagram because it's lower now. It has consequences, okay? So because my vapor pressure is lower here, I've shifted my boiling point to a higher temperature. So here is my boiling point of my pure solvent. Now that I've lowered the pressure, here is my boiling point now of my solution, where I have solute and solvent in my solution. So I've raised the boiling point. I also can look over here on the left-hand side of my diagram. As I lowered the pressure, I've also changed where my triple point occurs. So now if I look at this point right here, this is actually the point, is my freezing point here. But when I lower the vapor pressure by adding solvent, I also change the triple point here. So now my freezing point is actually lower. I have freezing point depression. A common example of freezing point depression, especially here in Alaska where it snows an awful lot, is actually by spreading sodium chloride and or calcium chloride on our roads. We actually lower the freezing point of that incoming snow so it stays liquid even at lower temperatures, and that is due to freezing point depression. An example of a semi-permeable membrane is the membranes around all of our cells in our body. An example of one cell is actually a red blood cell, and it is a water-permeable membrane, so it tends to let water in and out of it. So if I look at a solution, and we're going to call this a hypotonic solution, here I have a high concentration of solute inside my red blood cells, and I have a low concentration of solute outside the red blood cells, so for example in my bloodstream, the water tends to go into the blood cells and I tend to swell my red blood cells. If I go to another region of my body where I might have a high concentration of solute outside the blood cells and a low concentration in, the water will actually leave through that semi-permeable cell membrane and leave the cell. In this case, we have a hypertonic solution, and my red blood cells tend to shrink and become sort of crinkled. What we'd like to have is an isotonic solution where the concentration inside my red blood cells is the same as that outside my blood cells. Notice, again, that my solute, these sort of blue particles here, cannot pass through that membrane between the inside of the red blood cell and the outside of the red blood cell. If we look at cell membranes, they are very complicated structures, but they do contain these holes in them. That's what makes them semi-permeable. So we can have things like water actually be transported out through that holes in the membrane, and depending on the concentration inside the cell or outside the cell, I can actually build up osmotic pressure. Let's look at a graphic example of osmotic pressure. Osmotic pressure is defined as the amount of pressure necessary to prevent net passage of a solvent due to osmosis. In other words, passing through a semi-permeable membrane. So if I look at this U-tube here, on one side of my semi-permeable membrane, I have pure solvent. On the other side, I've actually added some solute to that solvent to make a solution. So over time, my water molecules will pass through that semi-permeable membrane, decreasing the concentration of my solute and building up pressure. And I can actually then just look at the levels here to actually measure that pressure. So we have a net transfer of solvent molecules to the solution side that will occur over time, and that yields an osmotic pressure that equals the rate of transfer in both directions. So once I've reached equilibrium, meaning my solvent is going in one direction at the same rate I'm going in the other direction, that's when I can measure this difference in level or the pressure that is built up due to osmosis. Scientists have actually found a relationship between osmotic pressure and the amount of solute in a solution, in other words, a colligative property. Scientists have actually symbolized osmotic pressure with the symbol pi, and that is equal to the molarity of the solution times the gas constant times the temperature in K. So we're going to represent the concentration of my solute in my solution by molarity in this case, times the gas constant, times temperature in K. In the example below, we'll actually use this relationship to calculate the osmotic pressure of a 1 molar glucose solution in water at 300 K. So pi again is my osmotic pressure. That's equal to the molarity of my solution, which is 1 mole per liter of glucose, times the gas constant in liter atmospheres per K mole of 0.08206 times the temperature of 300 K. Do the arithmetic. That equals to an osmotic pressure of 24.6 atmospheres. We can use this principle of osmotic pressure and osmosis to actually purify water. We call this process reverse osmosis. So if we set up an equilibrium where I have a semi-permeable membrane, I have pure solvent on one side, and I have a solution on the other side, if I apply a pressure to my solution side, I can actually force solvent molecules through my semi-permeable membrane, leaving my solute molecules behind and actually purifying my water. We do this all the time using either desalinization processes for actually purifying seawater. So if I take seawater, which contains a lot of solute and a lot of different stuff, both living and ionic, I can actually apply a pressure in the presence of a semi-permeable membrane and force the water molecules through that semi-permeable membrane to actually purify water.